The name of my talk is dark matter, but actually I will speak about problems and alternatives to the lambda solar matter model more than only about dark matter. Wait. Yeah. Well, the outline of my talk is I will speak about the lambda quadratic model. This is a review, very shortly. And after that, I will speak about the some problems of the lambda quadratic model and some alternatives. Okay, let me remind you what is the standard model of cosmology or the lambda quadratic model, the LCOM model. As you know, this is a space-time with a random elementary symbolic metric. The condensed demand of the model is dark matter with pressure equal to 0 and energy with a very exotic pressure equal to minus density, baryons with pressure equal to 0, and radiation and neutrinos with pressure equal to 1/3 of the density. But we have also inflation, from where we obtain the seed solution or the seed fluctuations forming the galaxies and the structure formations. We have also the Big Bang nucleosynthesis coming from the standard model of particles, and CMB, cosmic microwave background radiation formation comes from the fluctuations of the metric dispensing here. Well, the idea is to have inflationary times. After that, electrons and photons couple, and then there is a dark age. After that, we have a star formation, and after that, galaxy formation, and so on. But the main point here is how the galaxies form and how the structure formation take place. And the idea is the following. The dark matter fluctuations, or the dark matter fluctuation spectrum recombination is determined by a small number of physical parameters, very small number of physical parameters. And they start with very small fluctuations, and these fluctuations will grow up during the time of the evolution of the universe with collisions and with mergers. Well, after recombination, the amplitude of the baryonic fluctuations rapidly grows to match that of dark matter fluctuations. That means the dark matter forms potential wells, and the luminous matter, the baryons, comes into these potential wells and form the galaxy. That is the idea. And the smaller mass fluctuations grows to nonlinearity and virialize, and then are hierarchical cluster within successfully large bone systems. That means these small fluctuations will grow by mergers and collisions with other mergers, with other fluctuations, and they will form hierarchically. This is very important. Hierarchically will form the structure what we see in the universe. Well, and then ordinary matter in bone systems, total mass 10 to the 8, 10 to the 12 solar masses, cools rapidly enough within the dark matter halos to form galaxies, while larger mass fluctuations form clusters. This is the idea. The idea is very simple, and the idea works very well. Okay, this is the idea by now in numerical simulations. This is the Millennium simulation. You see, you have here a very homogeneous and isotropic, rather homogeneous and isotropic formation of structure, and this is in redshift 18.3. And after a while, you start to see this filamentary structure. This is in 5.7. And now you have this filamentary structure very hotter, and after a while, that means, for example, today, you have this filamentary formation very hot here. The formation is of these galaxies. Here you have the galaxies, the cluster of galaxies, and so on. The voids here, and so on. Well, this model works very well. You see, this is the comparison between the observations. Here, the points are the observations, and the line is the lambda quadratic model, the LCOM model. You see, this is the mass power spectrum, and the fit between observations and theory is spectacular, and especially here, this is the CDM fluctuations, the fluctuation of the microwave radiation, the temperature, and you see the fit is spectacular. But that means we have a really very, very good model to understand the universe and to understand the galaxy formation and to understand the cluster formation. Well, the candidates, we have some candidates to be the dark matter, and all of them are can be fit by or can be put by this formula. Here is the contents of the matter, the dark matter candidate, and in terms of the cross section and the velocity, this product should be very, very small, and therefore we say that the candidates are weak interacting particles, weak. And we have many candidates, the axioms coming from the strong CP violation in quantum thermodynamics, sterling neutrinos, for example. But the best candidates are the MSSM, the minimal supersymmetric standard model candidates, the neutralino, gravitino, and so on. Because from this, we solved it during this school that with this model we can solve the hierarchical problem of the particles. Well, how to observe these candidates is by detection of products of annihilation or decay of these particles, this is indirect detection, or by direct detection by interactions with nuclei in underground detectors. And maybe we have seen them. For example, this is the Gamma Libra of laboratory. This is a result. You see here this 6 months modulation of the observations of this laboratory. And the idea, the interpretation of this modulation is because the Earth is going around the Sun. And in one direction we will see an amount of dark matter particles, and the other direction we will see another amount of particles, and therefore this 6 months modulation. Of course, there are some criticisms about these results. The first one is that the background of the environment is not well controlled, and therefore maybe this is not an observation of dark matter, but observations of some local phenomena. And the other one is that these modulations implies that the dark matter, the WIMP, is between 10 and 100 GeV mass. And this is in tension with Shannon 200 results. We will see these results, and therefore many people don't believe in these results. Okay, but in any case, this is a first result. But other telescopes like here, this is the ICE2. Last week got ready. This telescope, they are tubes detecting neutrinos. They will see high energetic neutrinos in order to see the dark matter. You see, this is the Eiffel Tower. And maybe we will see in the next months, the first detection of dark matter, maybe. Well, other telescope is the Untitled telescope. It is very similar as the last one, but now this is in Mediterranean Sea, 2,400 meters deep, 4 kilometers far away from Toulon. And the problem with this telescope or this detector is that around of this, the Mediterranean, there are a lot of animals with electrical charge, and they are a big noise to be detected. But in any case, they will solve this problem. But other detectors, like for example the gamma ray with gamma rays, these satellites are detecting the gamma rays coming from the annihilation of these dark matter particles, and they expect to see soon these gamma rays coming from this detection. And you see there are many. This is in Namibia. This is the last satellite that decided since 2008, and this is MAGIC, and now they are constructing the MAGIC 2 in Japan. Well, and of course, the main detector will be the late LHC, where we will see the supersymmetry first, maybe the Higgs, after that the supersymmetry particles, and after that the neutralinos and so on. Well, we expect to have great time, exciting times in the next months, next years. Well, the delay detection is also carried out. This is the Shannon 100 observatory. And you see, this is the parameters of the theory. Here is the mass of the parameters, the mass of the WIMP, and here is the cross section. And you see this is constrained by these observatories, and now the supercode CDFS with 1 ton of germanium and flux with 3 tons of liquid shell and so on will constrain the parameters have. And you see, if we have problems with the 4 free parameters, the model, it doesn't matter, we will have another candidate, the second free parameter model, where we have these waves as well. And this is no, it is in the next time, in the next 3 years, 5 years, maybe we will be able to constrain all of these parameters very, very high. Well, this is a very nice time because we are able to detect or to know how dark matter may be, but now I will speak about some problems with the standard model, because the standard model is very, very well, but it has some problems. And I will speak about generic problems, not only special problems. Well, some of them are very old. For example, the strain fine tuning in the dark energy or the coincidence problems are very old. Cosby density, central density profiles and missing satellite problems also are very old. I will speak only about the dark matter problems, so I will list these 2, 1. But the new problems or the new observations last year tell us that there is no fit of the early ensemble of galaxies. There is some problems with galaxy because galaxy seems to be simpler than we want. Voids are too empty, no detection of dark matter, and so on. Well, let me first speak about this one. This is very old. You know, the galaxies have dark matter in the center. And normally this density profile goes like 1 over x. X is, for example, the distance divided by the linear radius or by the radius in 200 parsecs, so on. This is a simple parameter. And the observer one is between, thus the alpha is between 0 and 1. But the Navarro-White say that the density profile in the center goes like 1 over x. Maybe this is another profile, the anasto profile, this is not cosmology. But in any case, what we see in numerical simulations is always that the density is very, very costly. And the density is higher than what we observe. You see here some observations. This observation were made by the block. And you see, for example, this galaxy, this is the Navarro-White profile, and the observations show that the density should be here, or this one, or this one, or this one, or this one. Not all of them have problems with the Navarro-White profile, but some of them. And more recently, these observations here, these are galaxies, and this galaxy was observed till 79 parsecs, and this is the velocity. What we showed before was the density, but line velocity means a flat density profile in the center. That means that this galaxy has exactly a flat density profile in the center, and you see this fit cannot be done using the Navarro-White or the numerical simulation done by Collar Matter. Well, other observations here, you see those are the galaxies around us, our satellite galaxies, and all of them show a central density profile. This is a problem, but fortunately, we have some new numerical simulations made by the government, for example, and we will see here is the formation of these galaxies, the small galaxies, but now taking into account the environment and taking into account the other phenomena. For example, triaxial motion, or for example, a non-circular motion, or for example, explosion of supernovae. You will see here one of them, yeah, here, no? And for example, coming the structure from other regions coming to and colliding into this galaxy. And for example, here and here. And after all of these points, and after all of these feedback, what they obtain is that this galaxy now is very, very similar to the observer mass. You see here, this is the results, this is the mass, and the comparison between the numerical simulation and one observed galaxy. You see this is the mass and this is the velocity, and the fit is very, very well, okay? Then, well, maybe we have solved the problem, but there are two open questions. First, general results from several samples, including things and H1 surveys and so on, with high quality data imply that the three-axial and non-circular motions cannot explain the CDM Navarro-Fenway cost-score discrepancy. Well, this is a result of these astronomers. Other open question is that there is no evidence for internal future of star formation that could be the result of tidal processes or star formation induced by the closer environment. Therefore, okay, the problem is almost solved, but there are open questions. Well, you can say, well, this is a small question, this is a small problem, but now, you see, here I show you not only the governmental simulations, but many other simulations using hydrodynamics. And for example, this group here, where it's silent white ball, you see here, this is the many simulations. And all of them have exactly the same problem. You have here the mass of the halo, and you have here the mass of the stars, of the luminous matter here. And in general, when you form a galaxy, you will have an amount of luminous matter. And all of them have exactly the same problem. The dark galaxies formed in hydrodynamical simulations are almost 2 orders of magnitude more luminous than expected for halos of this mass. The observations are not coinciding with these simulations. Therefore, my opinion is that we are missing something. There is some non-physics involved here, and we have to be careful with that. Another problem is given by this group, led by Zavala. And you see, what they did is the following. Instead of the mass function, they took the velocity function. This is equivalent, but this is a little different, because the velocity function is determined by the free-falling objects. For example, the galaxies, they are free-falling into the cluster, and therefore they only need to know the velocity. And alfalfa, this Arecibo survey, is measuring the velocities of many galaxies, and what they obtain is exactly the same problem as before. The simulations with CDM predicts a steep rise of the velocity function towards lower velocities. For example, for velocities like 35 kilometers per second, free-falling velocities of 35 kilometers per second, the simulations predict 10 times more sources than the one observed. If confirmed by complete alfalfa survey, these results indicate a potential problem for the CDM pattern. That means we are missing, again, something in the information of the small galaxies, dwarf galaxies, LCOM galaxies, and so on. Well, other problems is the missing satellite problem. You know, around big galaxies like ours, there are a lot of small galaxies, LSB galaxies, and dwarf galaxies, and so on. There are many satellite galaxies. For example, this is our neighborhood. This is the Milky Way, here is the Andromeda, and we see a lot of small galaxies, around 30, 40, it depends on how you count. But numerical simulations predict 400, 500 satellites. Well, we can say, this is maybe a solution, is that these halos of galaxies are there, but we cannot see them because they are so small that they don't capture, for example, luminous matter or gas, maybe. Or maybe in the time of the recombination, or later, in the time of reheating, the halos were destroyed, the luminous matter were destroyed because of the reheating and so on. There are many solutions. Nevertheless, as we will see, this observation is not only for the satellites. Here we see another result for Disney. Disney took about 300 galaxies, all of them in different clusters, and he found that all of these galaxies, when they compare the different constants, different parameters of the galaxies, for example, the radius containing 90% of the mass, with the radius containing 50% of the mass, or the low luminosity, or the mass obtained by hydrogen, or the dynamical mass, and so on. All of them are correlated. But now this is a problem. Why? Because you see the galaxies were formed by hierarchy. That means by collisions. And all of them are, after many collisions, after this hierarchy, the galaxies are all the same, are all related. Therefore, they came to the conclusion that such a degree of organization appears to be also with hierarchical galaxy formation, a central tenet of the cold dark matter model in cosmology. Maybe, but maybe this is only one observation, but it is not. I show you these observations by Peebles and Musser. You see here the local cluster. Our local cluster contains about 560, a little more than 560 galaxies. All of them are here. And all of them are represented with different colors because all of them are observed by different observatories. In that case, some of them with 21 centimeters, other ones with optic and so on. Well, but here you see the local void, and the local void contains about 1/3 of the total of the whole space of this local cluster. And the problem is, you see here these circles, and these circles contain all the big galaxies on the cluster, and all of them are in the outskirts of the void. All of them, and all of these galaxies, these big galaxies, are exactly the same size, the same amount of matter, the same amount of clusters, of stars, and so on. They are very, very similar, again with the same problem. And they came to the conclusion that it is not clear why objects that might have been assembled in such very different ways for different ancestral objects should have had evolutionary tracks that conversion show small dispersions around simple power law follows from the size and velocity relations. Well, this is a problem. It's very similar as the other problem before. And Peebles and Musser came to the other conclusion that, in short, the general insensitivity of galaxies to their environments is not expected to standard ideas will help if galaxies were more rapidly assembled, as they could then evolve in more narrowly isolated universes. That means if the galaxies were formed more rapidly, then maybe they could solve this problem. Again, a problem against hierarchy. Hierarchy is on the top. Well, other problems here shown, and this is an observation of this group led by Collins. You see here, this is the growth lines here are the predictions of the millennium simulation. You see, this is the galaxies, the total stellar mass of galaxies given by the millennium simulation and redshift 1.5, 1, and so on. And they predict that the galaxies now should have 10 to the 12 solar masses. But you see, they see these red galaxies very, very far away. That means in redshifts 1.3, 1.4. And they see that exactly the same galaxies as today. And therefore, there is a problem. Again, this is a problem against hierarchy. This suggests a new picture in which brightest clustered galaxies experience an early period of rapid growth rather than a prolonged hierarchical ensemble. Again, a problem of hierarchy. Well, maybe it's not a big problem, but maybe it's we are missing something, some physics about that. Another observation, this is also for 2 years, and last year. This is another example. You see, this is a galaxy. This red point is a galaxy in redshift 2.3, very, very far away. And all of these points are normal galaxies what we know. And you see here is the dynamical mass versus the stellar mass. Here is the radius of the galaxy versus the velocity dispersion, dynamical mass, velocity dispersion, and dynamical mass and velocity dispersion. and radius. And you see, here, you see that this galaxy, very, very far away, is very similar as the other ones when we compare the mass. But when we compare the mass against the radius is very small. And here, the dynamical mass compared with the radius again is very, very small. That means that this galaxy is so big as the galaxies today, but it's much more denser. It's very, very dense, and they formed not only one, but many galaxies. The galaxies in got reaching 2.3. And you see all of them are very, very dense, but so big as today. So it's massive as today. That means that it seems as when the galaxies were denser, but with the same mass before, and they will grow up, but only in size, not in mass. Well, this is maybe a conclusion, but we have to wait for more observations. Other problem, and I never thought that this would be a problem, but well, this is the bullet cluster. You know, bullet cluster is the collision between two clusters. This is a big cluster, this is a small cluster. This is the X-rays observation, and this is the lensing observation in blue. Well, Mastro Pietro and Burkett made some numerical simulations in order to reproduce this cluster. And they found that the morphology of X-rays maps, the height of the project temperature jump, and the displacement of gas peaks are best simulated by a 6-to-1 cluster. That means this is 6 times bigger than this one, with initial velocity of collision about 3,000 kilometers per second. Well, that is well. That means that these two clusters collide starting with 3,000 kilometers per second velocity. Well, they had a little small problem, but this is maybe not so important, that the only way to fit the observational data using Navarro-Renwright profiles will be to assume the mass ratio is smaller. That means 2.7 against 1. But with this relation, they will not reproduce the X-ray data. But this is maybe a small problem. The problem is that these two guys, Matos and Lee, did numerical simulations, but now in a very, very big volume with 27 gigaparsecs. And they wanted to find some collisions like this one. And they found with this numerical simulation that the probability of finding 3,000 kilometers per second collisions is between 10 to the minus 11, 10 to the minus 9. That means very, very, very sensitive. It's very, very difficult to get some collisions with so velocity. And you see, this is another cluster discovered in 2008, and this cluster is similar to the bullet cluster. Therefore, in nature it's not so certain that you have such clusters, but it seems that numerical simulations tell us that this is very, very interesting. Well, that's another problem. And maybe I can speak now further about these problems I will escape that. Well, we have 3 alternatives. The first alternative, maybe the best one, is to remain with the Lambda quadratic model and to look for new physics in order to solve the problems within the Lambda quadratic model. And that is very good. I think this is a very good way to follow. But we have also 2 alternatives, and this is we can find or we can look for extension of the standard model of particles or of the general relativity theory. Well, we are not the first. The standard model extensions are, for example, self-interacting dark matter, warm dark matter, super heavy, ceramic, decaying extra dimensions, extra symmetries, repulsive, fuzzy, Kaizen, scalar fields, and so on. This list is, of course, not longer complete. It's only an example. And from the other side, we have extensions. Again, the scalar field can appear here or here. And this is the modified Newtonian dynamics. This can be seen as an extension of the general relativity, F the air, extra dimensions, and so on. Well, we can classify them, so I will try them very, very shortly in this, in these colors. I will take these two pairs. These those are the particles and extra dimensions. Well, let me start with self-interacting dark matter and warm dark matter. They are very similar. But what we have here is if the dark matter has self-interaction, then the self-interaction of the head of the dark matter will avoid that the dark matter collides into the centers and will avoid this cosmic central density profile. Also, this self-interaction and head will avoid that avoid the formation of small structure. Therefore, this dark matter candidate can solve this main problem. Well, you see, I show you here some simulations, some fits from these two theories, self-interacting and world dark matter, and they are fitting the centers of some small galaxies, the SSB galaxies. You see, they fit the galaxies very, very, very well. Therefore, maybe this is a very good candidate. Nevertheless, there is a problem. You have here this quantity, this is the density, and this is the velocity dispersion to the cubic, and this quantity can be derived by the cross-section of the self-interaction, or can be derived from the head of the world dark matter. This quantity should be a constant in each of these ones. But in order to fit the rotation curves in the galaxies, we have to put very, very different values for the constant. You see, these are different galaxies, the galaxies before, and this Q is used in order to fit the galaxy. And you see, for different galaxies, you need to use very different Qs. And therefore, the conclusion of this group is that the inferred cores do not provide motivation to prefer world dark matter or self-interacting dark matter or other dark matter models. Well, nevertheless, this is a good model. Those are good models, but maybe they have some problems. Well, let me speak very, very short about super heavy and self-analyzing the kind of dark matter. Super heavy is also called Wimsillas, and they are very close related. And Wimsillas, and they are very good candidates. But we can constrain them, all of them, using the Pamela constraints. Pamela is observing anti-protons against protons, the anti-protons and symmetry. And you see, this is the observer one. And those are the constraints against all of these models. You see, for different values of the models here. They are not very hard constraints, but what happens in which we mix the constraints of Pamela together with the Fermi constraints, and then this is very hard to fit them together. You see here the predictions of different galaxies, or the predictions for the galaxy M31. And these are the constraints of Pamela, and these are the constraints of Fermi. And you see, in order to fit both constraints, it will be very difficult to do that simultaneously. Therefore, the conclusion of this group here, these guys, is that these results put strong constraints on the possibility of ascribing to the kind dark matter both the increasing positron fraction reported by Pamela and the high energy features of the electron-positron spectrum measured by Fermi. Well, they are living, but these models are living, but they are very, very hard constrained. Well, let me speak very shortly about extra-deep symmetries. In principle, the MSSM model is a kind of these models with extra symmetries. We are taking the standard model and we are adding the supersymmetric group in this standard model. But there is a more simple way to do that. Why not to start with a dark group, for example, a dark gauge group, whose particles interact with the standard model only via gravity. This is very, very simple. Therefore, this is very beautiful because this model is very, very simple. And the gauge coupling constant becomes strong at lower energies. It will fit the elementary dark fields together with the phase transition or condensate scales lambda c above the scale the particle of massless, as in the standard model. At the condensation scale lambda c, they acquire mass, like in the standard model, of order of lambda c. But these particles are interacting only with the rest of the particles in the standard model through gravity. The elementary fields will form gauge invariant particles to the strong coupling. These particles are dark mesons and dark baryons, and they can account for the dark matter and for the dark energy. For example, let's take the SU3 gauge group acting only gravitationally. And this group has 6 chiral and antichiral fields with 97 degrees of freedom, a condensation scale of 42 electron volts, and an inverse power potential for the dark energy given by this power law with n equal to 23. This model gives a warm dark matter with free streaming scale given by this 0.6 megaparsecs, and an equation of state given by the minus 0.9, and with the right amount of dark matter and dark energy. Therefore, this so simple model can account for the dark matter. Well, this is one example of extra symmetries. Other example is if you add, for example, this SU11. This is like a Lorentz group. SU11 symmetry, the most general Lagrangian with this symmetry is given by these scalar fields. And if we write them in terms of spinors, we can obtain the most all the invariants of this Lagrangian and this Lagrangian. With this invariance, you can build the most general scalar field potential, and what we obtain is this potential, and you see this is plotted here. And the idea is the following: if you start in a system where the system is here, and drives very slowly to the minimum, and starts to oscillate and goes to the maximum because this is a Lorentz group. And with this idea, this travel from here to here is inflationary, and you have inflation, the right inflation, by the way. And with this oscillation, you will have dark matter. And the driving from here to the other the point gives you the dark energy. This is a very nice unified theory of all of these scalar fields, or the information scalar field and dark matter. Well, now let me speak about, we are speaking now about the scalar fields, but I will speak about repulsive, Fuzzy, Chi-sense, and scalar fields together, because all of them belongs to exactly the same thing, and I will spend a little more time, because these scalar fields, this Mont and FDF picture and the extra dimensions, all of them land in the scalar field paradigm. Therefore, I will speak about that. Well, the idea of all of these models is to have gravitation together with scalar field, and the way to model, to make different models from this idea is to propose a scalar field potential. For example, there are a lot of candidates. Here you see this for Peebles called fluid dark matter, and this one coming from landscape superstrings here, or this one coming from very general scalar field Lagrangians and so on. Well, the idea is very simple, because you have a scalar field and the universe is expanding, then the scalar field will condensate sometimes depending on the mass. You see, if you have a very tiny mass, a very small mass, the condensation temperature will be very big. And if you have a big mass, the temperature condensation will be very low. Well, the scalar field fulfills the Klein-Bottom equation, and when the potential has a minimum, when the scalar field goes to the minimum, it starts to oscillate. This is the oscillation of the scalar field. You see here a sum of these oscillations. The oscillations give the energy, and the energy gives you the dark matter. This is the plot of the densities. This is scalar field, the dark matter. This is the radiation, neutrinos, dark matter, baryonic matter, and dark energy. And you see this plot is exactly the same for the cold dark matter paradigm. That means that from the cosmological point of view, scalar field dark matter or all of these scalar field dark matter candidates and cold dark matter are exactly the same. Well, let me show you the features of the differences of these scalar fields. You see here, this is the evolution, this is the equation for the evolution of a perturbation of the scalar field. I will write here instead of the potential, I will write here the mass, because it's the mass. Well, and you see, and I perform a Fourier transform. Well, this is the evolution again, but now in terms of the Fourier transform. And you see here, this K is depending, it gives you the size of the fluctuation given by here. If this K is small, then this term is negative, and this equation will have only growing solutions, because it is negative, the negative part is dominated, and therefore this fluctuation will grow up. But if this K is small, is big for small fluctuations, this term is positive, and this equation will have only oscillating solution. Therefore, this is the first feature of the scalar fields, is that the mass power spectrum, scalar fields have a cutoff in the mass power spectrum. And that means that, these scalar fields have no problem with the formation of source structure, of the satellite problems. This is solved by this. You need to put here that the mass is 10 to the minus 22 electron volts, very, very many mass. Well, the second feature is that numerical simulations show you that the preferred mass to collapse of these scalar fields is given by this formula. Of course, if we put, again, the 10 to the minus 22 electron volts, the mass of collapse of these scalar fields 10 to the 12 solar masses, like a halo of a galaxy. That means that the halos are the fluctuations of the galaxy. One fluctuation is one halo. Well, that's the second feature. The third feature is that, if you perform a weak field limit in the Einstein equation and solve the Einstein equation, for example, the spherical symmetry, you will find that the galaxies predicted by this thing contains a flat density profile. This is the comparison between, this is Navarro and Y, this is the isothermal halo, isothermal profile, and this is the scalar field profile. Scalar field and isothermal. Therefore, if there is cusp in galaxies observed, this model can be ruled out. Well, and therefore it is possible to fit very well galaxies with this paradigm. You see here many big galaxies, or small galaxies, because you have a flat density profile. This is for LSB galaxies. You see, you can fit them very simple. Well, the last feature, this is also very interesting, is you start again with this equation, the evolution of phi, and make this transformation. This is a functions transformation, where you appears this S, and with this function you can define a velocity using the gradient. Well, but the thing is that this equation, the equation of the evolution of the density perturbation, becomes this one, and you can show that this S, the derivative with respect to time of this S is very, very small, therefore we can drop out them. And after that, we obtain a very, very similar system like in aerodynamics. This is very, very simple because you can know aerodynamics. And the only difference is this term here. Well, for example, if we suppose that this density and the S depends only on time, then this is 0, this is 0, this is 0, this is also 0. And therefore you obtain only this equation, and the solution of this equation is trivially this one. And therefore the density at the cosmological level goes like dust, like dark matter. Therefore dark matter and cold matter and scalar matter are exactly the same at cosmological level. Well, now let me show you what happens if we make a linearization of this equation in order to see the linear regime of perturbations of this system. We perform this linearization, you make this answer, and the difference here, this is very similar to the colder matter system. The difference is this velocity. This velocity is the only way, or the only part of all of this system where the Planck constant appears again. And this is velocity. Instead of that, in the colder matter, you have here the velocity of the sound. That means 0. This is very small, and therefore, if you manipulate them and obtain the equation for the density contrast, what we observed, the density contrast for scalar field matter is given by this formula, while for colder matter is given by this formula. This is the observed one. Well, you see they are exactly the same, but only the difference is the vacuum, the velocity. But this velocity here is the sound velocity and this quantum mechanical velocity are very small, and therefore when you perform the plot of these two together, they are exactly the same. There is no difference. Therefore, scalar field matter and quantum matter from the linear regime of perturbation are exactly the same. From the cosmological point of view, are exactly the same. The difference is done in the non-linear regime of perturbations, exactly where the quantum matter paradigm is having some problem. Well, other candidate essence is very similar as a scalar field, but now when the Lagrangian depends on this x is constructed by using the kinetic energy of the scalar field. Of course, if you have more degrees of freedom, you have more freedom for fitting observations. Well, let me summarize scalar field and matter with only one free parameter. Fits the evolution of cosmological densities, the rotation course of galaxies, and the central density profile of OLSP galaxies. With this mass, the critical mass of collapse for a real scalar field is just 10 to the 12 masses, the observed galaxies. The central density profile of dark matter is flat. The scalar field has natural cutoff, though the substructure in cluster of galaxies is avoided naturally. With the scalar field mass of 10 to the 22 electron volts, the amount of substructure is compatible with the observed one. And the difference, if we want to compare this with the colder matter, the difference between scalar field matter and colder matter is that scalar field matter forms galaxies earlier than the colder matter model, because they form bosons condensation to this temperature. And so if scalar field matter is right, we have to see big galaxies at big redshifts. This is the main difference between these two paradigms. Well, now let me go to MOND, to the modified Newtonian dynamics. This paradigm is very simple. You have the second law of Newton, and what they claim is that we change here not only mass times acceleration, but the function of acceleration. And this function changes dramatically when you have a very small acceleration, like 10 to the minus 8 centimeters per second square. Then this formula will violate nothing. This is very nice because they can fit the rotation curves of galaxies very, very well. You see, these are fits of these galaxies, of these different galaxies. Nevertheless, for a cluster of galaxies, they have a little problem, and they had to postulate a small amount of dark matter. A very small amount, but a dark matter. Well, this is not the problem. The problem, I think, is that this theory is non-covariant. It's not covariant, and the Einstein equations are covariant. Therefore, in order to relate both models, you have to make covariant this theory. And of course, it appears a covariant theory. This is the TVs, the tensor vector scalar density, scalar theory, with this Lagrangian. Well, as Dario said, this is very funny because in order to have this theory, you have to postulate a scalar field and a vector field together. And from this, of course, you can derive the amount, but you have to add two terms, two kind of matters, the scalar field and the tensor field. Well, this is again not a problem. The problem is that, as we saw yesterday, with this group could measure with lensing and with rotation curves could measure this quantity, and TVs predict very, very far away from the observed one this value. And therefore, we can say, well, we can rule out this model, but unfortunately, not yet. What happened? This group came to the rescue. What happened is, instead of to have here a density, a function of the acceleration, we have a function of the force. And in that case, the force it depends on the radius, and therefore this is a function of the scale. What happens then if you propose a function of the scale, and these guys claim that with this function they can recover the Newtonian dynamics, the Mont paradigm, the early Mont paradigm, and not only that, with this function, because they are working with scales, for big scales like clusters, they can recover the fit of the motion of the galaxies around the cluster without dark matter. Well, this is like a cockroach that you are trying to kill with your chew and never die. Well, these theories they came to the rescue, and I think we have to wait a little more longer to see what happened with this theory. Let me end my talk with the FDR function, FDR candidates. FDR are mostly used for dark energy, not for dark matter, but they can also be used to predict some kind of dark matter. This is the FDR. We have seen this Lagrangian many times. This Lagrangian is equivalent to this Lagrangian. And with this Lagrangian and varying the H, the Xi field, we can obtain this Lagrangian. And this Lagrangian are equivalent. And this is the Brandstrom Lagrangian. And if we perform the same techniques, but now with Palatini variation, that means supposing that the connection and the metric are independent, then with Palatini you obtain a little different Lagrangian, but you have also FDR lands again in the scalar field paradigm. You see, you have here a scalar field with all the things. Well, these FDR are very well for cosmology. You see, this is the angular power spectrum and the mass power spectrum given by the FDR. They fit very well. Nevertheless, the problem, as we saw today and yesterday, is that this Brandstrom theory is not compatible with local observations, because this omega should be very big. And in order to have FDR, we have to put here 0 or minus 2/3. Well, 3/2. Well, we can go around this problem by two ways. First, we can perform a conformal transformation like this one, and this Lagrangian transforms into this Lagrangian. This is exactly the same what the people working in superstring theory made. They landed all the time in this Brandstrom theory, but they perform a conformal transformation and obtain this Lagrangian. This Lagrangian has no problems with local observations, only that they have an interaction between matter and scalar fields. And therefore, this is a little different than scalar field. Well, the other way to go around of this problem is, let's write again the Klein-Gordon equation, but now in the Brandstrom theory. And you see, this is the Brandstrom, the Klein-Gordon equation, and this term is extra. But this term here is actually the density here given by this one. This is the metric in the Einstein frame, where you don't have scalar fields interactions. This is in the Brandstrom frame or Jordan frame. Well, therefore, you can put these two terms as a new effective potential. You see, this is an effective potential, and this defines a new mass for the scalar field. And what happens? Well, what happens is the following. Suppose you have originally this potential here, that is here, with, for example, a very small mass or whatever you want. And now you are working in a place where there are a lot of, a very big density, for example, in the galaxy or in the solar system. Then the density is given by this line here. Or you are working, for example, in a supernovae, and the density is bigger. Well, then the effective potential will sum both lines, and for example, for this case, the effective potential will be this, and for the other one will be this, and the mass is in the minimal of the potential is bigger, and here is bigger. That means that the scalar field acquires a new mass, and maybe with this new mass they can fit the local constraints. Well, this is under work. We will see how they get that. But by the moment, this group of astronomers look for these consequences of the chameleon field. This is the chameleon field. And they didn't find nothing in this paper. Well, but this is preliminary. We expect to have more news about that. Let me end with extra dimension. About extra dimension, we have heard a lot of things. But the idea in extra dimensions is also that if you have two brains, for example, we are living in this brain, and here this brain contains also a matter, and contains some kind of matter, and these two brains are connected by gravitation. But you have here perturbation of this matter. This gravitation, this matter will, these people living here will feel the gravitation by potential wells coming from this brain. In this case, we will not able to detect at all the dark matter. The dark matter is living in the other brain. And what is that? Wherever you want. Okay? This is another idea, and this work by many people. This is one example, and so on. Well, conclusion. In my opinion, the conclusion is very simple. We have a very, very good model for dark matter, but the question, what is dark matter made of, is open. We don't know that. And we have a very, very good, very, very nice candidate, but the question is open. We are working hard together in order to find some candidate to solve all these problems. But in any case, we are living very, very exciting times. We are in the threshold of the new era of cosmology, science, and thought. And my last word is enjoy it. Thank you.
Questions?
So maybe it's just a comment. You showed a lot of possible alternatives to the CDM paradigm. You probably forgot to mention one, which is dark interactions, which is somehow related to the F of R model that you just showed, but it has some significant differences actually. And as I briefly showed in my talk last Monday, also dark interaction models can predict a lot of features that would somehow alleviate the tensions of the Lambda CDM. For instance, we showed that it predicts shallower density profiles than the Caspian FW. We have emptier voids. We have a lower baryon fraction in clusters, and we also have higher velocities in the cold dark matter field, which could also somehow alleviate this problem of the bullet cluster and so on. So it's just a comment to tell that there is another possibility.
Yeah.
Or questions?
So, in some of the alternatives to cold dark matter, like the self-annihilating dark matter, would you have would that produce some kind of radiation that you would then be able to observe?
What do you mean, with the scalar field or something?
No, when you talk about self-annihilating dark matter.
Yes. Analyzing dark matter should have this radiation from any kind of radiation. It depends on the candidate you have, and with that radiation you have to be able to detect this part. Yeah.
So because we don't see that, is that not really? I mean, is that still a theory?
Yeah, no, the theory is living. You can say you can work in this theory as well, but these constraints, the Pamela and the Fermi constrain very, very hard these theories, and you must be very, very careful which candidate you propose because the constraints are very, very hard today. But it's not ruled out. Not yet.
So with these modified theory alternatives, shouldn't the first test that you do see if it can match the bullet cluster observations? Why worry about doing anything else until it's satisfied that? It seems like it was.
Well, the people working in this modified Newtonian dynamics plus the new, they claim that because these smaller clusters are in the scale of clusters are very big, and they could fit these velocities 300 kilometers per second by free fire. And this is another the things they claim to solve, for example. But I don't know. For me, it's also difficult to believe this kind of theory.
More questions? Well, I used to say about theories, I know that people, Marisa Calariado, just did a paper just confronting theories with the same parameters that fit the rotation course of galaxies in the Mond lineage. They show that using the Thebes version is incompatible with the lensing. So, right, Thebes is almost ruled by these arguments. Right? More questions? Comments? Okay, if not, we see you here at 4:30. Thank you. We thank.
Yes.